Okay, guys. Hi, hello, everybody. This is Mark here. And let me tell you hello. Like, here's me, right? Okay. I'm doing a couple things that are not standard today. First of all, I'm presenting from the Linux, from my Ubuntu, which is just a better environment for developers. So I chose not to go to Mac. And what I want you to do is to confirm that you hear me okay, and then you can see my screen okay. Here you are, okay? So just confirm that in the chat, for example, you should be able to do the chat. Okay, so you can see my screen, and that, Sherry, you did in this. I'll say thank you. There you are. And you can also hear me okay, right? I'll go open the chat window for myself. And I see yes. So you can all hear, you can all see, and for me, it's just a bigger screen, so I can tell you more and better information. Okay, so we will start. Yes, the recording will be available later. You see Sharon, she is a great organizer of all of that. So you will be able to ask questions and she may answer or I may answer. So I will see that chat. You will not see my window chat, but I should be able to see a chat. Okay, that is great. And you're all welcome. I think that is an interesting topic here, judging by the number of participants. So I'll be verifying, I'll be checking on the chat once in a while, but here we are ready to go. So here's our subject today. We'll be talking about high performance Python. And I said that the first unusual thing is that I'm presenting from the Ubuntu, but it seems to be okay. The second thing is that I don't want to be too formal. When things work right away, well, it's kind of a little miracle, but nobody is learning anything. So I'll allow myself to go rough and something might not work. That's on purpose. Okay, so I will be showing you how we go through the slides. My plan is this. I want to talk about the class. It really is a class, but that class becomes a webinar right now. And I will also tell you about the actual subject, the high performance Python. I will also do some of the labs. So we're going to get the complete workout. If later on you want to continue learning, I'll show you what my recommendations are. So let us start. We are all here. That's high performance Python. If we are talking about the way I usually teach it in class, then that's what the goals are. We assume people know Python. I just saw it just really a few minutes ago. I saw that finally Python made it to be above Java. So it used to be the third language. According to some now, it is the second most popular language. So Guido van Rossum, that's the guy who invented it, deserves the praise. It's interesting that it was a side project for him, but by now I won't stop on that too much. So we assume that people know Python, and that exactly is the problem. Because Python is what they teach you in school, in the university. That is what everybody expects you to know. And so very many people start doing Python without too much programming background. And the problem is that it works at first, but then you run into all kinds of problems. So I'm welcoming you guys to chat anything that you can about raising the problems. I also see that Ken raised his hand. So what should I do for the raised hand, I wonder? Maybe I can unmute. Nah, that's too much probably. You can ask, Ken, if you want to say something, you can ask the questions here, okay? And I see somebody did say something. Okay, so we all see everything. Let's continue. So that exactly is the problem, that Python is so easy and that too many people know that. And as the result, what happens is that you start your wonderful new project in Python, but you are sometimes not a professional programmer. So you lack the discipline. You don't do testing. You don't do testing first. I'm sure many people would agree that that is a must today. And then later on, first of all, the code is not maintainable because people don't like to work with your project. It's not documented. It's not tested. And secondly, it begins to work slowly. So some person has to be assigned to that, and they don't want it. So all of these problems are not only technical, they are also people problem. Let's talk about what we can do about this, because by now I hope you all agree that it does happen. So here you are. We assume that you are already comfortable in Python, and many of you probably more so than I am, but it's still an open area, the performance. So what I want you to do is bring you to this, how do I improve it? How do I do the good architecture? That's one of the things that a must. You must be able to write nice code, not just code, a project that people will not mind maintaining. In fact, they will enjoy maintaining this. So that's our goal. And it usually, such a class is usually 4 to 8 hours. That's not that much. Maybe just because today people are not into spending too much time in front of their computer. Now, if I ask you guys about how much percentage-wise, let's say 8-hour work day. No, I know it's not 8 hour for you, maybe, but how much time do you spend in front of your computer? And you can put it as a question here or just in the chat. That's my question. 8 hours, okay. 6, 7, 10, that's honest, sometimes more. Okay, so that's a lot. And today I now notice that many people ask us, can you please do a half-day course? We just don't have the time to concentrate for the whole day. So that is a kind of new course generation for those kinds of people. And that particular course also includes visualization. We're not going to go to visualization. So instead we will do a lot of labs. That is what we usually do. This guy is he has to press the any key, doesn't know where the any key is there. So I'll explain where this is. Now that picture is my fault. It should say I know Python and optimization, but you will know something at the end. So usually I ask you a few questions here. We don't have that luxury. Instead, we'll just go and start our slides. So the real slides are coming right here. Let's close this one. And let's start this one. And as a way of introduction, as I already told you, Python is very popular. So lots of people use it. When they use it, what they really do is using the CPython. That is an interpreter. CPython is called CPython because it's written in C. So it's efficient, but it's not efficient overall. It's only efficient in each individual operation. And so it's well known that it will be pretty slow when we're talking about real performance. When we're doing one conversion at a time, let's say 2 times 2, of course, it doesn't matter. But when we're talking about pretty hard to compute code, when we're talking about something that gives real workout and load to our computer, then performance becomes important. And so first of all, you need to have good structure. Yes, you need to have good project, but you also need, after all is said and done, you need good techniques on how to optimize your performance. So you don't want to be this guy who is banging his head on the keyboard. And for that, there are ways and approaches. Well, basically, the approach is the same as for all other languages. You profile first. You're finding that place, which is a problem, and you're optimizing that place. But there are a few more things to talk about here. One of them, again, is because Python is so easy. So there is very little attention paid to the good structure and much less even to profiling and how not to waste time anywhere. That is what we will come to. But first, I'll need to give you a code to run. So the first thing that I will do, I will say, yes, I'll show you how you do profiling. That's a must. I'll show you how you can see that graphically, how you can find out where the problems are and how you can fix them. But at first, we'll need some code. So here's the guy who says what we should start with. And what we should start with is the code should work. You're right. When you were writing your code and that code was working, great. That was actually a good goal to strive for, because you shouldn't optimize. At first, you should not leave it for later. At second, following Scott Myers, who wrote the C++, effective C++, a second step you also shouldn't optimize, and the third one you shouldn't. It's only later on when things are really problematic and you can then profile it, then you see that, boy, I do get the problem, I need to optimize it. So what you do is this, you make it run and you make it right, but then you need to make it fast. We are today concentrating on this third step. So here's what I'm going to give you. I'll give you the code. And in my case, what I'm going to do is I'll show it. I'll do a demo because it will be too much for you guys to actually run it right now during the short webinar that we have. The expected duration of it is maybe 40 minutes and then questions and answers. So I'll give you some code. I will show you how that code runs and loads the system. And then we'll try to improve it. What I'm going to give you is the code that will simulate a particle. Here's a particle. And that particle is moving on the circle. Every step that it takes will move it a little bit, in this case, to the left, but that really depends upon direction of velocity. And every step will be an iteration. So if I have, let us say, 1,000 steps, I got 1,000 steps to run. And then if I add another particle, that will be 2,000 steps. And if I now add 1,000 particles, now I get 1,000,000 steps. That will load the program and it will run for a few seconds, and that will be good enough for us. So that's my plan. I'll do that. I'm explaining how we go step by step and how we're going to first do the good programming practices, and we will create a class. That class will encapsulate the particle idea. So in the constructor, we have that couple coordinates and the velocity that it has. That is what we're going to start with. Now the velocity in this case goes almost perpendicular. We go back here. I'm not giving you the direction of the velocity because the direction is always like that. We are doing a circle, and to create a circle, we always need to go in the same direction. So that's what we're doing. That's why you only see one parameter for the velocity. If you make it bigger, it will run faster. If you make it smaller, it will run slower. Now, I'm checking the chat just to see if there was something. Okay, everybody is happy. Let's see that. How about chat? Question answers. Okay, we're all good. Wonderful. Thank you so much. Okay. Well, one quick chat really. Do I see all of the chat? Maybe you are saying something over there at the bottom. No, we're good. All right. So that will be the code I will load. That will be the next position. And you see we are doing some of the operations here. We're saying that the next position will be distance from where we are, the distance from 0 times the speed. And note that that will probably later on will be a good way, a good place to optimize, because here we're doing x squared plus y squared and then a square root. So we will question if that's the good place, but that is in this particular case because we know the code and we know what it does. Other cases, we will absolutely have to profile. So that's what we will do. We'll calculate direction of our motion. That is our particles, they're moving. We will calculate what is the next position, and we'll go and do it until we're done. So that is the plan. Well, if so, we need to then have a few particles. And these particles, well, all of them will be moving. So that's the plan. First of all, we can initialize this particle simulator by giving it the constructor, the self, and the particles. Those particles will be a collection of our particles. So particles we just described, that's where they are. That's individual particle. Those particles will be a collection of those guys. And now to move them around, to evolve, we'll have to say that let's go with a certain time step, a small one, so that we can load the computer, do that many steps, and this is pseudocode. We're not doing it really, but calculate the direction, calculate the new position, and do it again and again, over and over. I am sure you're familiar with Python, that it says that in order to use your loops, you need to avoid doing open close parentheses. That's what C and Java do. But instead you put the colon here, and then you're one tab to the right. That's within this loop. Then another column, another tab. So you're in this loop. And those people who don't know Python then can see that that really is a loop. And then there's a loop inside this loop. And these are the three things that we do. Well, that's exactly the danger of Python. It's just so easy. It's so easy to read that nobody pays attention to performance. And later on that bites you. That's what we're coming to. So in our case, we will set up the access. We'll create the initialization where we will have a few of those particles, and we'll start running. Now, that code also shows one interesting thing. Once you use the plotting, the standard plotting of Python right here, then you can change the position of the particles, and that will still be reflected in the plot. The plot does not generate one little picture. It generates as many pictures as you want. Not everybody knows this about Python, but that is where you will see the code running. All right, so that's the complete visualization. That's the last segment of the code that I'm showing you. What we're doing is this. We're creating a simulator. We're creating the collection of those particles. And then we are creating a plot, and we're animating that. We're going to evolve with 0.01 second step, and we're going to animate this. Good. Well, I want to test that. I want to visualize this test. That will be the test visualization. That's enough code for now. So at this point, I really need to run that lab and show that how it runs. Here's what I do. I go to my place where we store all of our labs. They happen to be on GitHub. So it's right here for me. These are my solutions. Now, they are not open. Don't try to get them right now, but I will give them to whoever wants. I don't want to open it right now. In the class, I usually do just because it's easier, but here is what we're going to do. In each of those individual labs, there will be an instruction. That's what I want to open right now. First of all, we need to model the reality, and that's what we have done so far. We said that the reality consists of particles, and those particles are moving around with a certain speed. So here you are. All these steps, they tell you what you need to do. And the way I formulated this is in the real lab, you would be copying that code. You would say, all right, what do I need to do? So create a directory called modeling. So let's do this. Let's create a directory called modeling. So let's say maybe we'll make a directory webinar. And inside of this webinar, we'll create a directory called modeling. And now we'll go into this modeling directory. Here we have nothing there. So it says now you will create your first model. I'll create it in the simul.py using VI. And I'll start inserting this code. If that's what you do, then it really stays with you. Ideally, you should even type it. You know, there is a book called Learning Python the Hard Way, a very popular thing. And it says you should never copy paste, but instead I should type from matplotlib import pyplot as PLC. Now, for the purposes of your uh, not being bored, I'm copy pasting. But when you are going through these labs, of course, I do recommend that you do as I say, not as I do. You copy more. This is the class called particle. So at least when I do this, then I at least understand what I'm doing to a certain level. That's better than just running examples. So here we are, that's our first particle that we're imitating. Now we want to model this particle motion. That's the particle motion, that's the simulator. The simulator will do it for every particle. You remember the pseudocode. Over there it said 1, 2, 3. Well, now it gives us the real code that will simulate the particle movement. So I can do this here, and now I got this code. Now the beautiful thing, of course, will be if I don't do it right and if it crashes. That's nice because that will teach us something. But if I do everything right and copy paste, it will probably work. So now I need to visualize it. If I run it this way, it will already run, but I won't see anything. So that's not interesting. I'm using this visualizer, as I told you, where I'm connecting my data to the plot and I'm putting it on the plot. Let's see what will happen when we do this. Okay. So I said we need a test function to observe that. So here is our test function. That's the last thing that we need in our code. And in real life, that code will take us some time. That's not an obvious thing to do. In our case, we assume the code is already there, already written. What you're doing is optimizing this. So we more or less understand now what the code does, and we're seeing that's our main. Our test visualizes our main. So we save that, and according to following the instruction, we're saying Python run this code. Let's see how it runs. Beautiful. It didn't work. Let's see, where did it not work? Angle velocity. Let's check. Which line was it? Hard to say. So guys, you are very welcome to help me. So it complains about angle velocity. Let's see. Here it is, right? And it says no such thing as angle velocity. Well, what's my particle? That is my particle here. So let's go back and see what does it have. Angle speed it has instead. All right. So we have two choices. We can call it velocity, or we can change that for speed. Let's check how many changes I would have to make. Okay, that's only mentioned here. How about velocity? Okay, so it's my choice what I can do. I'll follow this. So instead of velocity, I'll say speed. Speed. And here, I'll do speed. Okay, let's try to run this. Python. All right, okay, wonderful, works. With some suspense, we saw that it works. So we can use this. Let's see how much load we're putting in our system when we do this. Probably not much anyway. Let's bring up the monitor. Here it is. Okay, we're using our CPUs more or less. Should we give it more work to do? It will run better. Well, let's watch what happens when we remove that. Let's stop our application. Let's see how much load do we remove. Seems about half. So we're good. That was our first step. Let's go back to the slides and see where we are. So we said, first of all, let's model the reality. And if we don't know good programming practices, that's the time to learn them. You should name your variables consistently and nicely so that anybody else, not only you, can read it. You remember one of the founders of computing, he said, the guy who invented C, it's Kernighan. He said, it's not that hard to write the code that computer will understand. Writing the code that humans will understand, that's much harder. That's what you need to do. So I showed you how you encapsulate all of the elements, how you have functions and variables inside of the class, and how you try to break your modeling of the reality into some reasonable classes. In our case, we had particle simulator, and then programming practices came and we did testing. All right, so far so good. If you guys have any questions, you will ask those questions. I'm checking no questions so far. Next step. The next step is also very important. You would think, let's go and optimize. Let's run the profiling as soon as we possibly can. That's not true, because what we're going to do is optimize our program, and we're going to try a lot of different optimizations. And meanwhile, we'll break our code for sure. I showed you code that didn't work in the first place, and these labs were called solutions. So how much more so we will break our code when we're optimizing. Therefore, the second step, the must step, is a good test suite. I'll show you a good test suite. It won't be complete at all, but every time you try to iterate, you're verifying that you haven't broken anything. That's the good discipline. So this is what we will do. We'll take 3 particles, we'll run them, and then we will ourselves will calculate the results. So we'll need to test it with the test evolve. I'll show you what I mean. Let's take those particles, let's give them some initial positions, and let's move them for a little bit. Let's move them for a certain amount of time. Once we do that, each particle will get its own new position. Here I'm checking that particle number 1, that its x position became this. Well, how did I calculate this? Well, I probably ran this program, so I rely on that program itself. However you come up with the tests, but you need a lot of them so that any inexperienced programmer who comes into your code and runs these tests, he first of all sees that right now the code is good. And secondly, once he or she starts changing this code, then it is still good. Now, my personal experience is one guy came to maintain my project, and the first thing he did was turn out all tests because they, annoying right in the middle of his work. Well, you can imagine what happened. I'll tell you the practical life story. So he kept moving and things were working seemingly. And then he said, okay, I'm now doing a big change. He never got to try, just purely never. We had to go back very many iterations because by now nothing really worked. And I believe that's because even he is a brilliant programmer, but programmers have this tendency of running too fast. And so let me run to the next feature. Well, great, but please don't turn off the tests. So that will be our test. We need to prepare the test, make sure that it runs. We will also need to prepare a further step. That further step I'll show you in the next lab, not in this one. But the further step will say, okay, now what am I going to optimize? So first of all, a good design model. Secondly, a good test suite. And finally, benchmark to optimize. I'll come to that. That will be in the next lab. So that will be the benchmarking code. I will run it for 1,000 time steps, and we'll verify what's the load. We'll time that. We'll see how much time does it take to move 1,000 times, and maybe for 1,000 particles, because you see that here we're setting a particle with a random number and we're moving it 1,000 times, so 1,000 particles. That will be our benchmark. So we're good there. So let's do this. Let's first of all do the testing, and secondly, prepare for real benchmarking. Okay, let's do this. Let's go to the testing lab. The testing lab is all right here. Testing. And all of them have their own instructions. That's the instruction. And it says now, do this. Prepare a new directory. The new directory will be called testing. And to avoid all the problems with building a copy of previous code into this directory. So that's what we're doing. Let's take it away. Here, we're good. What we did was this. We just ran this wonderful demo. It worked. We know it good. Now we need to create the next step. So here we are under modeling. Let's go up and let's create a directory called testing. Let's go into this directory and let us copy the Python module from the previous directory. So copy from modeling to here. Now we have this thing. We can run it here. Let's just test it that it still runs even though we're here. So it doesn't depend upon directory. We're good. We can run it. Now the next step is, what does the lab tell us to do? So here we are. The lab says prepare the next file. The next file will be called test evolve. So create that file. Test evolve. And again, I give you all of the code to run. So it's interesting that we're saying import those particles. Now, the structure of Python is such that building large packages requires certain skill. In this case, the previous package is under simul, it's there, so I can do this. I should be able to do this. If I'm not all that certain about my Python skills, I will stop right here and I will try to run that far. And what does it say? No main. Well, it's fine, of course, no main, but at least it imported without any problem. I believe so. All right. So we continue and we're adding more code. That will be the testing code that I want to add. That will also be the main. So I'm adding that code right here. And let's see, what does this code do? This is the testing code. It tests and verifies that we get to the absolutely right place. So let's do this. Our main will be this test evolve. So we should be able to run Python, test evolve, and what didn't work? Doesn't match anything. So let's look at what our problem is here. Not sure what it is now. I don't want to keep debugging everything here, but I know something. I know that this is a solutions part of the labs. So if I look at that, then I will see the complete code and I will see that I didn't do it right here. You see, that was all the way to the left. I didn't do that. So I can risk it and just move it to the left and see if that works. If not, I'll copy the whole thing. If not, I'll just run it right there. So first of all, let's do the simple way. Here and here. Let's try to run it now. Still didn't. Okay, there are many little things. I'm not gonna try to fix all of them, but instead I'm taking all of that code. I'm editing my previous attempt here, and I'm deleting all that I have. And I'm putting this new code right here. Let's see if that runs. It did run. Now, meanwhile, I have some questions from you guys. So let's look there. Chat. Aha, thank you for the tabs. Okay. That's right. If you want to just, yeah, thanks for that advice. That's great. And you're saying you'll wait for the slides. And I will wait for you asking for them. So that's a courtesy game. But in any case, here's my test. So I ran it. I verified that those tests are good. But let me test something else. Let me change something. Let me verify that if I ruin something, then it won't work. So maybe instead of here, instead of 0.1, and of course, being a good programmer, I'll make a copy. Okay, that goes out. I'm commenting this out. That's the real one. And here, I'll do something like this. Okay, so I expect the code not to work and give me some errors. Previously, it ran. It says, I'm running testable, any errors, no errors. So let's run it again. Ah, error. And where's that error? Line 126. Doesn't work. Well, I remember, and you probably do too, that that is the place I just ruined. So let's go back and put it back. Here we are. And I made a copy for myself, so I can just delete this line. I can put this one back and verify that we're still good. All right, that works. That was step number 2. And step number 3, we want to run the timers and we want to verify that things are good. So here we are. And now we want to time that program. So the easiest way is to just run this time. Let's go back and try it right away, immediately. Let's try that. So instead of just running this, we're saying time. We got what they said we should get. And we saw that, well, that's a faster machine here, I guess. Runs about 2 times faster. So we got the real time, the user time, and the system time. First of all, what are those guys? Here they are. The real time, the actual time spent for the whole process. That should be the largest. That's what you would expect, right? 0.408. The next one is the user, okay? Sorry. That's all the cumulative time spent by our CPUs plus the system. So normally you would expect CPUs plus the system, that's the total. So you would think that if you take that and if you add this, you'll get that. Let's check if that's true. In this case, it actually is. It's almost correct. 409, that's what I would get. But it could be different because there are multiple CPUs. So if you're doing something smart, it will count it for all of the CPUs. So it might even be bigger. But at least we see where we are. Therefore, which is the most important time here? Is it the first, the second, or the third one? If I ask you that question, what do you think? The first, the total time, all are important, and user time. So we have all guesses, all right? I would venture to say that it's the user time because that's my code. I probably cannot change much in the system, and real is pretty close to user plus the system, so I cannot change that much. But you're right, sometimes maybe there are very deep ways how I interact with the system, and maybe I can optimize that too. So I first look at user, and you would probably agree with me. I'll look at user first. But then maybe there will be ways to optimize the rest. By the way, going for the low-hanging fruit, the system time is 10 times less than the user anyway, so I don't really have to start there. Okay, we'll agree. That's the timing. But we want something deeper. You all guys know about timing. So there is a time it. That's already a bit more interesting. And that will run it for a few times. And it will run it for a few times and give you the average. So that's more interesting. Let's try that. Let's try to do time it. No such thing. That's because it has also run as a module. So let's go and look at all of the options that we can have. You can run it as a module in Python. You can run it as a Jupyter. So our labs will show you all kinds of timing. Now, right here, I'm not going to do those labs, but I'll show you what the essence of it is. And I will also show you the essence of the optimization. So now let's go to our labs and analyze them. Here we are, the timing lab. So timing lab is right here. And what we need to do here is this. First of all, we will get our code, the benchmark code, and we will run it. We did it. We saw that it works. We also timed it. We saw that that also worked. Now, if you're in Windows, you're kind of out of luck because time it doesn't exist there. But instead, what you can do is go to the end of that lab and you'll find out that there are tools for Windows that will imitate Linux. Cygwin is one such tool, and probably with new Windows, which has a simulation of Linux, maybe life is even easier. So here you are. That's what you do if you're in Windows. I expect you guys are on Mac. Somehow you tell me that. What's your computer? Aha, Karen, Windows, right? And Linux and Mac. Okay, all right. So I think you see a preference. You see that they like to push you into working on Mac and Linux. That's not a blasphemy nowadays because everybody's more or less. Okay, all kinds of environments. So keep in mind, don't fight it. Find a good environment. Don't try to overdo it, but the advice there exists. So that was for timing lab. Now we want to do something else. We want to do profiling. We will all come into profiling. By the way, in the timing lab, I think it was showing us all other different options. So here we said that you can time it by using time, or you can use IPython. Now, if I run IPython, it should probably run. Let's try IPython. Gives me a certain shell. In that shell, I can run it. Here's how you can do it. You can say import. Now I'm in IPython. Okay, and thanks for the comments. I really like that. So here we are in IPython. Import there, and well, I didn't do the benchmark as yet, but I should have done the benchmark and then I would time that. Okay, well, let's do it after all. We have a minute. Not such a big deal. I'll just steal that benchmark from right here. Here's the benchmark. So I'm just taking that code. Not that much code. And here we are. I should be doing it in timing. And there's no such timing. All right, let's do it the right date. Timing. Then go into timing. Then create this file called benchmark. And then let's put the code in there. So first of all, that should run. Let's check that it runs. It doesn't because I forgot to copy the other model. That's all real life things that normally happen to you. We're not perplexed or perturbed. We're copying it from the previous module here. It was called okay. I'll stop doing the demos. Demos never work. But if there was such a thing that I would be able to run here, run as suggested, I would run IPython, and that would give me a better interactive environment. There, I would be able to simply do time it, which didn't work before, but here I would do the time it. And then I would be able to do a lot of other things. That's because IPython is really the predecessor to Jupyter. So as a bonus lab here, as you can see, you can redo all of that in Jupyter. One more level of high-level thinking, that's what you would get to, because you probably know and love Jupyter. So can you do your performance optimizations in Jupyter? Yes. Does it have the timing? Yes, because it's based on IPython. So you can go up and use the existing packages, and now you're quite ready to do the optimization. So with that, we'll do just one more step on the slide, and we're saying now profile it. So you see, if I just told you go and profile it, then you would skip all the previous steps. And that wouldn't be right. That's why you really benefit from following the right order. And now we will go into this lab and we will run the profile. And that's how easy things will be. So we can try to do this command and see how that works. Let's go into our labs. Let's come to the profiling labs. And let's open the instructions. They're always right here. So here, that's how you would write this benchmark. Let's just try to run it, see if that works. I don't really expect it. I was rushing too fast, not copying some of the modules. So I will run it, but I'm almost sure no luck. Let's try that. So this is benchmark, but it's missing something. Let's go into timing. No, well, let's try that command, see how it fails. But if I had other things here, like the simulator, then it wouldn't fail and I would get something. Now I'm good because I can see an exact display of where things are, which line is the worst, which is the culpable line, and I can rearrange this display in different ways to see the parameters that really interest me. I can do more. I can save that into a file. So here's an example of a little bit different code where I run it and I save it into the file. And then a few tricks that you would have to install. You would have to install this, the call tree. You would have to install the cache grind. All of them are extremely easily installed in Linux. And on Mac, it's not all that easy, but the end result will be is that that's what you will see. Once you see this diagram, okay, then you know which line is the problem, which line you should experiment with. So in our case, on our slides, I'm suggesting a few improvements. After you've done all of that, all of the profiling, all of the analysis with the graphical user tools, now the question is, how do you really optimize? Well, that's how you optimize now. That's what we have come to. It took us 50 minutes, but there was no way out. I hope you agree that the proper order and the proper discipline is required, at least to be popular geek among your friends. So this is what will happen. You will analyze your algorithm. Most of the improvements come from the algorithms. I'll show you how you improve little things, but the big things is clear thinking. And that is not maybe even teachable, but at least you can try. So that's what you will do. You will try to rearrange, but then you'll go for smaller small gains. You'll try to see what are the number of instructions, how exactly do I go through my loop, what are my structures. You know, there is a well-known thing that the original Python list is a very slow thing because it is very generic, very general, and it is a linked list. And you need to go through every element of that to get to the end, as opposed to a vector, which is much faster. So you will read such things. You will read which structures are fast. You will start thinking about what is the order of operations on each structure. And in our case, I'll show you exactly what we do in that lab. But here are the other things that you will be looking for. But again, don't look at them before you start. First, the code should work. Then it should be nice and maintainable. And then you're looking at each collection that you're dealing with, the computation complexity and how you should deal with it. The lists and the decks, what are they and which one is better? Okay, sometimes you will optimize memory. We have not touched on memory optimization, but that's the heap. How long does it take to work with that heap? And the use of caching. So guys, that's pretty much an overview. My question is the last question. If you have any optimization experience, what was your war story? What was the most interesting thing? So I will ask this, any war stories in optimization? And now, unfortunately, I don't let you talk, sorry, because we're too many, but you can chat. Okay, if there are no more stories, that's fine, because that's why you're here. So now what's next? Not only what's next in optimization, what's next for you? I use time it. Okay, but there are more ways of doing it. Yeah, I agree, Sherry. Great, great. So what's next is go to Amazon and see what books are out there. That's what's next. Now, of course, you can come to my course, but I'm not really inviting people to do that because we teach usually for corporations. I never recommend people to just pay the corporate prices. It's good when your work sends you. Then, of course, send your boss to us. We'll do it. But let's see, high performance Python. Now, not every book is the same. I'll tell you my personal experience with the books. I looked at this high performance Python, and it has an extremely impressive authors, and they have improved it for Python 3. But to me, at least, the labs just didn't work. I wrote books myself, and I know human psychology, and you're lazy to do everything. So it looks good, and you leave it there. Now, I don't know how that happened. Okay, all great reviews, right? But didn't really quite work for me. The one that really worked for me was this. That was Gabriel Lanaro. That guy is a physicist. I think he's a molecular physicist. So he works a lot with optimizations, and all of his labs did work. What was interesting is that it didn't work out of the box. So I asked him a question. He was very nice. He answered the question. He said, change this, and it will run, and then it did. So that's the one I would recommend. I'll give you the link to that. And I'll put it here in chat. And now your question. So is there a consensus of what is considered clean code? I would venture to say no, there is none. It's all human. Do you like science fiction? Do you like love stories, or do you like Proust, Shakespeare, or Joyce? Is there consensus on which is better? I would still say it's very much Person dependent, depends what you like. I don't know, Karen, what you think, but it's really the writing style. The writing style of the programmer is clear thinking. So no, but ask other people. Like I have a friend, a programmer. He says, "Okay, we finished talking. How was my delivery? Was it on a scale of 0 to 10? How was it?" He says, "Well," I'm saying, "Okay, well, 7." Well, I should be very careful answering such questions because then he says, "What will it take to take it to 8 or 9?" Okay, I'm not trying it on you right now. It's not fair. You came for a nice webinar, that's all. Because I will immediately ask you, what would it take, right? But that's the idea. The idea is ask other people, Karen, and check what they think. Is your code clear or no? Very often it seems very clear to you, but no such luck for the other people. So, more questions. Good. So you know what to do. You know where to write. That's where you got the invitation to the webinar. You will get the recording of this webinar soon. You will get the slides, all the labs if you ask for them. And I just wish you good luck. It's a lot of fun doing what we're doing. So please continue on the journey. Goodbye now. Thank you all for coming. Yes, you will. Then you will automatically get a recording of the complete session. You'll get the whole thing. All right, as my friend says, giving you back 1 minute of your time. And thank you, Sharon.